Hello everyone, today we're going to pull back the curtain on a field that I believe is one of the great unsung heroes of engineering, power electronics. It's the invisible yet absolutely critical technology that makes our entire modern world tick. It's the silent engine inside pretty much everything you use, and we're about to see exactly how it works. I want you to think about something for a second. You plug your laptop into the wall, and what comes out of that socket? It's this raw, high-voltage alternating current, a wild, oscillating wave of energy.
And yet, the delicate, super-sensitive microchips inside your phone or your computer, they need a perfectly stable, low-voltage, direct current. So how on earth do we bridge that gap? How do we get from that chaotic wave to the gentle, precise sip of energy your electronics need to survive?
Well, the answer lies in a field I've been fascinated with my entire career. It's called power electronics, and it is, quite literally, the art and science of taming electricity.
You know, when you boil it all down, power electronics is about two things: control and conversion. It's about taking electrical power in whatever form it arrives in, and with incredible efficiency, transforming it into the exact form needed for a specific job. We're not generating power here, we're mastering it.
Now here's the amazing part. This entire sophisticated field is built on one of the simplest concepts imaginable, the switch. But let me be clear, we're not talking about the light switch on your wall. Oh no, not even close.
A mechanical switch is clunky, it's slow, it has physical parts that grind against each other and wear out. A power semiconductor switch, on the other hand, is basically solid-state magic. It has no moving parts, it can turn on and off millions or even billions of times per second without breaking a sweat. That speed and reliability is the bedrock of modern power control. And in our toolkit, we have a few key players. You have the diode, which is the simplest. Think of it as a one-way street, or a bouncer at a club, only letting current flow in one direction. Then you have the MOSFET, which is like a super-fast digital gate. You apply a tiny voltage and whoosh, it opens or closes almost instantly. Perfect for lower power stuff. And then you have the IGBT, the heavy lifter. It's a clever hybrid that gives you both speed and the muscle to handle the really high-power applications, like in an electric car. But all of that incredible speed comes with a catch: heat. A lot of heat. Even a tiny percentage of inefficiency, when it's happening millions of times a second, generates a massive amount of thermal energy in a very small spot. That's why a huge part of power electronics is thermal management. These massive heat sinks aren't just for show, they are the absolute life support system for these devices, pulling that heat away before they literally cook themselves to death.
Okay, so we've got these lightning-fast switches, and we know how to keep them cool. Now for the fun part. What can we do with them? This is where the real alchemy begins. By turning these switches on and off at precisely the right nanosecond, we can literally reshape electricity into whatever we want.
It all boils down to three fundamental conversions. We can change alternating current to direct current, we can change one level of DC voltage to another, and we can change direct current back into alternating current. If you can master these three transformations, you can power anything in the world.
First up, rectification, going from AC to DC. This is precisely what's happening inside that little power brick for your laptop. The circuit uses diodes as one-way gates to essentially chop off or flip over the negative half of that AC wave, smoothing it all out into the steady, direct current that microchips love. Next, DC to DC converters. This is absolutely essential for anything that runs on a battery. See, a battery gives you one fixed DC voltage, but the components inside your phone or an EV all need different voltages to work. These converters act like a sophisticated gearbox for electricity, chopping up the DC and reforming it at a new voltage, whether it's higher or lower.
And finally, the grand finale, inversion, going from DC back to AC. Honestly, this is the technology that's making the renewable energy revolution happen. A solar panel creates DC power. Your home runs on AC power. The inverter is that brilliant translator in the middle, using those fast switches to build a perfect AC sine wave from DC, ready to power your home or be sent back to the grid. So, now that we have these three fundamental conversions in our toolbox, we can start to see how they build everything around us. These aren't just abstract concepts, they are the building blocks that power virtually every single part of our modern infrastructure.
And the crucial word here, the one I really want you to remember, is efficiency. Modern power supplies are ridiculously good at their job, often topping 90, even 95% efficiency. Older, linear technologies would just burn off half their energy as useless heat.
The leap forward here saves a phenomenal amount of energy on a global scale, which means lower electricity bills and a smaller carbon footprint for everyone.
Take a look at industry. Power electronics are the heart of all modern motor drives. By precisely shaping the power going into a motor, you can control its speed with incredible accuracy. This is what runs factory robots, conveyor belts, pumps, even the elevator you rode today, all while using the absolute minimum amount of energy necessary.
And electric vehicles? An EV is basically a power electronics masterpiece on wheels. It's using powerful converters and inverters to manage this massive flow of energy from the battery pack to the motors, giving you that incredible instant torque every time you touch the accelerator.
This quote from the source material really just hits the nail on the head. You cannot have a modern green energy system without advanced power electronics. The two are fundamentally completely linked.
Just think about it for a second. The electrical grid demands stability. It's a finely balanced system. But the sun isn't always shining, and the wind isn't always blowing. Power electronics acts as that intelligent interface, that essential bridge that takes the chaotic, variable power from renewables and conditions it into the stable, reliable electricity the grid needs to function.
So as we start to wrap this up, it becomes pretty clear. From the smallest charger in your backpack to the largest wind farm on the horizon, power electronics is the quiet, enabling technology behind it all.
So let's quickly recap the most important takeaways. First, power electronics is all about the efficient control and conversion of electricity. Second, the entire field is built on the foundation of incredibly fast and reliable semiconductor switches. And third, these devices are the key enablers of our digital lives, electric transportation, and a renewable energy future.
And that leaves us with a final thought. Looking forward, we are in the middle of a massive global push towards electrification. The demand for cleaner, smarter, smaller, and even more efficient power conversion is just going to explode. The question for the next generation of engineers, for many of you, is not if power electronics will be important, but what incredible innovations will you unlock with it next? It's an exciting time. Thanks for listening.